Hello, class. This is Mr. Hart, and in this podcast, I want to continue the pressure and fluids chapter. And last time we ended off talking about atmospheric pressure, and we ended with the idea that high pressures will always push towards low pressures. Okay, they'll always push or flow towards low pressures. So we looked at the example of a water bottle. If you crushed it near sea level, where it was at a high pressure, and you brought it up towards the top of a mountain or something in a higher altitude, it would expand because there's a lower pressure on the outside. And so you'd have a high pressure in here, a low pressure on the outside. And so that high pressure air is going to push towards the lower pressure air. Okay. This can explain, for example, why a bag of potato chips will fill with air. If you've ever been in the grocery store and you buy a bag of potato chips and it's only a little bit of chips at the bottom and the rest is filled with air, it can be really frustrating, but realize that they aren't just filling it with air intentionally. It's because they package the chips in Plano, Texas, which is a lower altitude. Okay. Or at least Lay's packages them in Plano, Texas, which is a lower altitude. So when they bring them up here in Utah, it's a much lower pressure. So the bags naturally will expand because of that lower pressure. Okay. And so to us, it looks like they're filled with air. Okay. But that's not the case. Okay. That's just a natural expansion from air pressure. Okay. So if we want to look at how air pressure is affected by height, okay, in the lower atmosphere, we have a lot of particles, okay, that are in the lower atmosphere. So we say there's a high pressure, and the higher you go up, there's less and less and less particles. So you're going to have a lower pressure up here. It's kind of like if you ever done a dog pile on someone, the person on the bottom is going to feel the most force, right? Because they have more people on top of them. Okay, but the person on top isn't going to feel hardly any force at all because they don't have anyone on top of them. Okay, so it's the same thing with air. It's like a big dog pile. All the air at the bottom is feeling the force from everything on top. Okay, so it's always going to be high pressure at the lower atmosphere, but it's always going to be a lower pressure in the higher atmosphere. Okay, so high pressure, low altitude, low pressure, high altitude. Okay, so it's kind of switched if you want to think of it like that. But again, just think of the dog pile. Okay, high pressures at low altitudes, low pressures at high altitudes. Okay, so we did a lot of cool experiments looking at high to low pressure. Okay, I crushed a can using steam. So the steam is at a higher pressure than the surrounding area, so it pushed the air out. And then I'd put this can in the water upside down, and because the steam is cooling, it then becomes a lower pressure, and so the pressure from the outside would actually crush it. Okay, so if you want to see a video of that, go to this link. Okay, so that's a cool example of air pressure crushing a can. Okay, we talked about the egg in the bottle experiment. You can also find that here. Um, what it does is they light and match inside the bottle, which kind of eats up the oxygen. So you get a low pressure in here and a high pressure on the outside compared to it. So it actually pushes an egg through the bottle. When that egg usually wouldn't fit through, but because of the air pressure, it can actually force it into the bottle. So that's a cool experiment as well that uses high to low pressures. Okay, we talked about we talked about how strong it is. They actually do the same thing as the can crushing experiment, but they do it with a steel drum. So air pressure is even strong enough to collapse a steel drum. Okay, which is pretty cool. This is another example, another video of them doing it in slow motion, and they record it in slow motion so you can see the drum actually collapsing, which is pretty cool. Okay, so we did a lot of experiments. Last one that we did is I filled this balloon with air, and then I plugged it on the outside, and it actually stayed full because the pressure on the inside of the globe was low, and so the high pressure from the outside actually keeps the balloon inflated. Okay, I didn't do the water trick, but I filled it with air, and it still stays inflated from the high air pressure. So that's another cool example as well. Okay, and so another interesting application. This is rail car cleaning. Okay, like I said, this air pressure is pretty dang strong. Okay, so when they clean rail cars, they use a steamer with some nice hot water and chemicals, and they're steaming out the inside of these freight cars and stuff. When they do that, you don't want to close the the freight car. You don't want to close the latch because you want that steam to naturally settle out. Okay, if you do close it, this is what could happen. It could collapse that rail car because that once that steam and all those chemicals cool, they cool down, creating a low pressure. So the high pressure on the outside can actually implode those rail cars. So that is pretty cool. Okay, that's that strong. But that's what not to do. Okay, for your rail car cleaning. Okay. Um, and then the last one, as we watched this video about gas nozzles, how they work from different pressures. So I also recommend that one, how they know to automatically turn off when the car is done fueling. So I recommend watching all those videos. They're all very cool examples of air pressure. Okay. Then we talked about what atmospheric pressure is measured in, okay, or what its value is. So they defined a unit called an atmosphere, which is just the pressure of the atmosphere, basically. And so it kind of makes the math easy or the description easy because you can say the atmospheric pressure is 1 atmosphere. Okay, simple enough. But if you want to look at the actual units for that, it's actually 101.3 kilopascals. And if you remember, a pascal is a newton per meter squared. Okay, so it's 101 of those. There's 101 newtons per square meter. Okay, that's pretty strong. That ends up being about 15 psi or 15 pounds per square inch. So every inch has 15 pounds of pressure on it, okay, around us, which is pretty amazing. So another thing we want to talk about is how did we figure that out? How do we measure that atmospheric pressure? Okay, and so what we use is what we call a barometer. Okay, and so you put a vacuum in here, vacuum meaning low pressure, right? No air. Okay, and so you put a vacuum in the tube and you fill it with something like liquid mercury. Okay, or some type of fluid. Okay, so you get this low pressure out here, and then that means there's going to be a high pressure on the outside trying to get in to that vacuum, right? So it's going to push on this fluid as it tries to get up to that low pressure. And so based on where this fluid is, okay, you can tell where the pressure is that day. So if the fluid's right here, you might say, oh, that's normal pressure. If the fluid goes up like this, you might say, oh, that's really high pressure for the atmosphere. If it goes down to here, you might say, oh, it's a low pressure day. Okay, so the atmospheric pressure can be measured by looking at where this liquid is, right? How high up it is or how low it is. Okay, the stronger the pressure, the higher up the tube it's going to go. Okay, so we call that a barometer. Okay, so there you go. That's all we want to cover for atmospheric pressure. Let's go on to fluid pressure. Okay, or what determines air pressure. So again, air is pressure, right? Or air is a fluid, so it exerts a pressure. Okay, just like any other fluid. We want to look at how, in general terms, any type of fluid exerts a pressure. Okay, so not just air, but water or oil or other types of substances, other types of fluids, liquids or gases that exert pressures. And so we want to be able to calculate this. And so the equation we use is what we call, well, I don't know what you call it, but basically it's how the pressure varies with depth. Okay, so the pressure P is going to be equal to the density of the fluid, rho, times gravitational acceleration, g, times the height, or in other words, what we would call the depth of the fluid. Okay, so, and again, I apologize for the bad spelling on the touchpad, but the depth of the fluid. Okay, so again, the pressure is equal to the density of the fluid times gravitational acceleration times the depth of that fluid. Okay, so this is for any fluid: air, water, oil, milk. Okay, any type of liquid or gas. We can calculate the pressure based on that pressure or based on that fluid's density and its depth. Okay, so let's look at an example problem really quick. So what is the water pressure at the bottom of a 15-meter deep lake? Okay, so if I want to find the pressure, that's going to be equal to P equals rho G H. Okay, in this case, we know that it's water, right? So if you remember, the density of water is 1,000 kilograms, 1,000 kilograms per meter cubed. Okay. And then we know that the gravitational acceleration is 9.8, okay, meters per second squared. And then the depth or the height is what it gives us. Okay, so it's going to be equal to 15 meters. Okay, so you plug those all in. Okay, I'm going to pull out my calculator really quick. But if you plug those all in, you get 147,000. Okay, 147,000. Okay, and again, the unit's going to be pascals because this is a pressure. Okay, so there you go. It's a pretty simple equation, right? All you need is the density of the fluid and the depth of the fluid, and you can figure out how much pressure that fluid's exerting. Okay, and so pretty powerful equation. Okay, so if you're doing this for participation, try answering this question. Okay, so what is the water pressure at the bottom of your 1 foot deep bathtub? So in this case, you're going to have to convert it to meters first. Okay, 1 foot into meters, but then it's pretty much the same equation. So try and answer that if you're doing this for participation. Okay, and then try it one more. Okay, so one really cool application of this is when they build dams, for example. So like the Hoover Dam uses enough concrete to withstand a pressure of 2.2 megapascals, right? 2.2 million pascals. Okay, that means it can withstand 2.2 million newtons for every square meter. Okay, that's a lot of strength. Okay, and it's even more than that. Okay, in some of the places. But using that information, we can actually calculate what the height of the Hoover Dam is. Okay, so if we know that it can withstand that much pressure, okay, we know P equals rho GH, okay, or the depth, right? If it can withstand that much pressure, that means it can withstand that much pressure at the bottom of that dam, okay? And so we can rearrange this so we can actually solve for the height of the Hoover Dam. So if we divide by rho and divide by G, okay, we get P over rho G, density times gravitational acceleration. That gives us the height, okay? So this is really cool because we can plug in how much pressure it can withstand, the density of the water and gravity, okay? And we can actually figure out what the height of the Hoover Dam is. And so that's pretty cool. And if you actually do that and you calculate it all out, I think it ends up to be around 73 meters, which is about 220 feet, okay? So it's pretty tall, okay? Or no, wait, hold on. Sorry. I think it ends up being about 220 meters, correct. Let me just plug that in really quick just to make sure. Yes, sorry. I'm mistaken. It is about 220 meters, okay, which is about 700 feet, okay. So Hoover Dam is pretty tall, okay, but you can actually calculate that using this pressure equation. So that's pretty cool that we can use such a simple equation to figure out the height of the Hoover Dam, okay. So really a powerful equation, really useful equation, okay. And then last thing we want to talk about is water pressure. So I won't have you do this problem, but if you've ever been inside your house and you've turned on the sink and you've ever had low water pressure, okay, it kind of stinks if you've ever had that situation. So we're glad that we have nice, strong water pressure, okay? And that's because of we have water towers that make sure we have this nice, consistent water pressure. And so the standard water pressure in American homes is around 340 kilopascals. And so if you use that pressure equation, you can actually calculate how tall water towers need to be. Okay, and so when you actually do that out, you get that water towers usually about 30 meters above a normal American house. Okay, so again, a really cool application of this equation. We can use this application or this equation to figure out how tall water towers need to be They use it when they design water towers so they can figure out how much pressure that water tower is going to give to all the homes. Okay. And so, again, you want to make sure you understand this equation. It's a really powerful equation. We use it a lot. And again, it just can find the pressure for any fluid. Okay. And so hopefully that makes sense. Let me know if you have any questions, and thank you for watching.